Section 1 remote learning lecture video. This is the only section in Chapter 9 we will be covering, but please keep in mind this is a bit of a doozy, so it's in your best interest to make sure that you're going along with the slides, doing your reading, and generally following along. So in Section 9.1, we're going to be talking about this concept of hybridization. So hybridization is a term we use for kind of understanding how covalent bonding is occurring. So when you think about it, we know that covalent bonding happens between the valence shell electrons in different atoms. So if I have a carbon bonding with 4 hydrogens, like in the molecule CH4, I know that there are the valence shell electrons in the carbon, there are 4 valence shell electrons. And if you draw the electronic configuration for carbon, we know that there are 2 valence shell electrons in the 2s orbital and 2 valence shell electrons in the 2p orbital. In a hydrogen, we know that there's only 1 valence shell electron, and that valence shell electron exists in the 1s orbital. So how exactly do these electrons that exist in these different orbitals, the 2s, the 1s, the 2p, how do they share with each other? How do the atoms share those electrons if they're in these different kinds of orbitals, these different shaped orbitals? So that's where we're going with this, is this idea of hybridization, this idea that instead of having s orbitals and p orbitals, we get these combined hybridized sp orbitals. So that's what we're going with this. The fancy way of saying this is the mixing of native, or the naturally occurring atomic orbitals. The 1s, the 2s, the 2p, the 2p, 3s, 3p, so on and so forth, like we've always done with our electronic configurations. But they mix in a special way, and they hybridized. So one of the type of hybridized orbitals that we'll talk about is this sp3, which literally means 1 s orbital and 3 p orbitals, for a total of 4 orbitals. It's formed from 1 2s orbital and 3 2p orbitals. Again, think of your electronic configurations. If you were to draw the electronic configuration for carbon, right, with your little boxes and your arrows, you would have 2 in your 2s for valence shell electrons for the carbon, and 2 in the 2p. Atoms that undergo this process are said to be sp3 hybridized. So we're having 1 from the s and 3 from the p. So altogether, you would count 1, 2, 3, 4 total atomic orbitals to make these 4 sp3 hybridized orbitals. Oop, I just got the pinwheel of death there. Sorry about that, folks. Let's see if we can get back on track. All right, there we go. Sorry about that. So what does this look like? Here's a 1s orbital. We know 1s, or any s orbital, for that matter, could be the 1s, the 2s, the 3s. We know the s orbital is spherical in shape, and that the p orbitals are going to have these kind of dumbbell shapes to them. Now, when we get to Chapter 7, we'll talk about this in a little more detail, these shapes and everything like that. For right now, you don't have to worry about it too much. Just understand that when we say we have 3 p orbitals, we're talking about 3 dumbbell type shaped orbitals, one that lies in the plane of the x, one that lies in the plane of the y, and one that lies in the plane of the z. It's hard on a piece of paper to draw this, but remember, these things take up 3D space. So these are the atomic orbitals. There's 4 of them, 1 s orbital and 3 p orbitals, for a total of 4 atomic orbitals. When they hybridize, we get 4 identical sp3 hybridized orbitals, 1s and 3p. And these, when they all are kind of lumped on top of each other, give kind of an arrangement that looks like this. You might notice we're getting our tetrahedral shape back out of this. So think back to our example of CH3. CH3 has 4 bonds, right? 4 bonding groups, 4 electronic groups for a tetrahedral shape. 4, 1, 2, 3, 4 hybridized orbitals. Each of these orbitals is what's going to go make one bond with the hydrogen from the carbon. So let's look at this in terms of those energy orbital diagrams, right? So we were saying earlier, think of this in terms of our electronic configurations, right? If I'm talking about a carbon, we know that it has the 1s down here, but we know that the valence shell electrons are at the 2s and the 2p, right? So in a carbon, there would be 1, 2 electrons in the 2s and 1, 2 electrons in the 2p. So we would take our 1s electron and our singular 2s orbital and our 3 2p orbitals, and those will be hybridized into 4 sp3 orbitals. And it's important to look at this energy diagram. This is done purposely. We know that 2s is lower in energy than 2p. But when they hybridize, the orbitals that come out, they're slightly lower in energy than the 2p, but they're slightly higher in energy than the 2s. And now they're all at the same energy. This is important. This allows us to share those bonds equally, right? When you look at CH4, there isn't, some of the CH bonds aren't more energetic than others. They're all equivalent to each other, and that's because they hybridize. So whenever an atom requires a set of equivalent tetrahedral atomic orbitals, again, think of CH4, this model assumes that the atom adopts a set of sp3 orbitals. The atom undergoes sp3 hybridization. And it would look something like this. So again, the green represents the carbon, the blues represent the hydrogen. The carbon, we know, had 4 valence shell electrons, and those 4 valence shell electrons existed in the 2s and in the 2p. Those 2s and 2p's hybridized into 4 identical sp3 orbitals. And each one of those sp3 orbitals will go make a bond with one of the hydrogen atoms, the S from the hydrogen atoms. And that's how we get our CH4. So this is your first door question. I'm going to leave it right here for you. If you need to pause or you want to think about it, go ahead. So let's look at this. Let's describe the bonding in an ammonia molecule using the localized electron model. So what we just did with CH4, I want you to now do with ammonia. So if you want, pause the video here and try and draw out the Lewis structure for ammonia. That's the first thing we're going to have to do, because we're going to have to figure out the geometry before we can really move on with this. So we first need a Lewis structure, like I said. That's going to be the first thing we need to figure out. Once we have a good Lewis structure and we've checked formal charges and everything like that, we know we have a good logical Lewis structure, we're going to look at the arrangement of the electron pairs, right? We're going to figure out the electronic and the molecular geometry using VSEPR. And then lastly, once we have our geometry, we can figure out the hybrid orbitals that would account for that shape. So here's our Lewis structure of NH3, right? Ammonia, we know, has 3 bonds and 1 set of lone pairs on the nitrogen. So that means we have 4 electronic groups around the nitrogen, our central atom. We also only have 3 bonding groups. So we know electronically this is tetrahedral, and I'm going to leave you guys to figure out the electronic shape. That was just on your last test you just took, so hopefully you remember that. Oops, sorry about that. Oh my goodness. Determining, so a tetrahedral, again, just like in our CH4, there's going to have to be electrons living in 4 different areas. So that means we would need sp3 hybridized orbitals to make this occur, which would mean that our N in our NH3 molecule is composed of 3 sp3 hybridized orbitals, and one of those, the 4th sp3 hybridized orbital, has the lone pair in it. So the lone pair is hanging out up here in this orbital, and the other 3 are then sharing electrons in these bonds. We know that there are other shapes besides tetrahedral. We can have sp2 hybridization. So this would be when we have one s orbital and two p orbitals combining. And this would give us a trigonal planar arrangement. We know that in trigonal planar arrangements, there are three different areas for electronic groups. Three different areas, S, P1, P2, 1, 2, 3. That's how we get sp2. Just like in sp3, there's 4 bonds, right? 4 electronic groups around here. That's how we got a tetrahedral arrangement. 1 for the S, and then 1, 2, 3 for all 3 P's for a total of 4. That's how you need to look at this. So when we have trigonal planar, for example, you can think of BF3 or something like that, we know that one of our 2 p orbitals isn't being used. So again, right, because we only use 2 of the 2 p orbitals, and we know that there's always 3 p orbitals. So that unused p orbital is just going to hang out. He's going to stay a p orbital. He's going to continue to look like a dumbbell, or a bow tie, some people say. And sometimes that unused p orbital will be used to make a double bond or a triple bond, but we'll get to that in a little bit. You do not need to remember that it's the pz or anything like that. Just know that one of the p orbitals is not used. So in this case, right, here's our atomic orbitals, the s and 2 of the p's. They hybridize together to make, right, 1, 2, 3 went in, 1, 2, 3 have to come out. And because there's 3 of them, they're going to arrange themselves in a trigonal planar arrangement. And then we can make 3 bonds from there. Again, what we're seeing here is we have these 3, right, the one singular S and 2 of the P combining together to form our sp2 hybridized orbitals, and then that unused 2p orbital just kind of comes around for the ride. He's not hybridized. He's just going to hang out up here in a higher energy state. So this is what it would look like. These yellow orbs represent the sp2 hybridized orbitals. They no longer have the s looking like a sphere or the p's looking like the dumbbell, right? Here is our unhybridized 2p orbital that's just hanging out. He still maintains his dumbbell-like shape. So now that we have this unhybridized p orbital, we can start talking about the different kinds of covalent bonds that form. This is different than talking about polar covalent and nonpolar covalent. This is talking about what types of overlaps are occurring when the electrons are shared. We have a sigma bond, which is represented by this little symbol here. Sigma bonds are when electron pairs are shared in an area that line up between 2 atoms. So anytime we have a sigma bond, it's going to be a single bond. So anytime there's a single bond occur, so basically if we have CH4, all 4 of those bonds, right, there are 4 bonds between the carbon and 4 individual hydrogens, each of those bonds would be a sigma bond. A pi bond, which we represent by the pi symbol, is overlap between unhybridized p orbitals. This is how we get double and triple bonds. So we know when we draw a double bond, we have 2 lines, right? One of those lines is the sigma bond. The other line would represent the pi bond. For the purposes of our class, it does not matter if you make the top the sigma bond and the bottom the pi bond, or vice versa. As long as in a double bond, one of them's a sigma bond, one of them's a pi bond, you've done it right. So what does this look like? Let's look at, for example, the compound CH4. I would like you to pause the video here and draw, C2H4. I would like you to pause the video and draw the Lewis structure of C2H4. Draw it correctly. So pause here and draw what you believe the Lewis structure of C2H4 should look like. Once you have your Lewis structure, hopefully you've recognized that there's a double bond between both of the carbons and a single bond between the carbon and each of the hydrogens. So when we look at this, we would say, okay, this individual carbon, when we look at its electronic geometry, it has a electronic group with this hydrogen, electronic group with this hydrogen, and there's a double bond between these 2 carbons, which means this is just one electronic group as well. So this carbon and this carbon, because they're symmetrical, both have trigonal planar structures, which means their going to have sp2 hybridization to them. But how did we get that double bond? We're okay, hopefully, with the idea that these yellow ones here are representing our sp2 hybridized orbitals, and that we get a sigma bond when we have the overlap occur here. But we know there's a double bond. How is it making a double bond? How is it sharing more electrons? Well, it shares more electrons by having the overlap of these two orange unhybridized orbitals. Now, a lot of students like to make the assumption that the tops and bottoms are separate. This is all one thing. It's just a funny shape. It's just a dumbbell shape. It's all one thing. So for this to overlap with this, the tops and bottoms have to overlap. So an sp hybridization. So we've done sp3, which is where we have 4 bonds, tetrahedral. sp2, where there are 3 bonds, trigonal planar. And now we're going to do sp. 1s, 1p. 2 electronic groups. What shape does that have? Linear. So this is when we have one s orbital, a singular s orbital, and a singular p orbital doing hybridization. And a good example of this would be in carbon dioxide. We know carbon dioxide is linear. So go ahead and draw your Lewis structure of carbon dioxide. So I'll pause here for a second for you to do that. Pause your video. Carbon dioxide, we know that we have carbon in the center, oxygens on each side of it, doubly bound to that carbon. So we know that's a linear molecule. There's double bonds. So we know there's 2 sigma bonds and 2 pi bonds. How did we get that? We get that because there are 2 unhybridized p orbitals in the carbon. So let's look. Here's our s, our singular s and our singular p. They hybridize. We have 2 atomic orbitals go in, 2 molecular orbitals have to come out, and so they make a linear arrangement. So this is our carbon, right? And then this can go make a sigma bond with one of the oxygens, and this can go make a sigma bond with one of the oxygens. We still have 2 of our p orbitals that are hanging out that are unhybridized on the carbon. So here's our carbon with its 2 sp orbitals. Right now, don't worry about the sp2 on oxygens. We can go back and look at those in a minute. But this would be just the sigma bond to one oxygen, the sigma bond to the other oxygen. So that's 2 single bonds. We know carbon needs 4 bonds, right? So there are 2 unhybridized p orbitals that can now overlap, right? This is representing it here. Here are the 2 sp hybridized orbitals that went and made single sigma bonds with each oxygen. And now we have these 2 leftover 2p unhybridized orbitals on our carbon that are going to overlap to make those double bonds. So this is what it looks like. The blue in this case represents the hybridized orbitals, right? Sigma bond to an oxygen over here, sigma bond to an oxygen over here. Now remember, this isn't 4 different orbitals. This is 1 orbital, 2 orbitals. Okay, so one of these is going to go make a double bond with the oxygen over here, and one of these is going to go make the other one's going to go make the double bond with the oxygen over here. And so we draw it like this. These lines are just kind of representing that the unhybridized p orbital of the oxygen is overlapping with the unhybridized p orbital of the carbon, and same with this one and this one. So sigma bond, pi bond, pi bond, just like that. So I would like you to try drawing the Lewis structure for N2 on your own first before we begin, and determine the electronic geometry. So this would be a good time to pause on your video and draw out the Lewis structure for the molecule N2. So we know that the Lewis structure for the N2 molecule is each of these nitrogens, they have a triple bond between the 2 of them, and each of them has a lone pair. So when we look at a nitrogen, we see 2 electronic groups, one group here and one group here, which means this nitrogen, and by default because it's symmetrical, this nitrogen, are both linear. If it's linear, that means it's sp hybridized. 2 electronic groups, sp, 1, 2. So each nitrogen atom is only using up one s and one p hybridized orbital to do this, which means there are two leftover unhybridized p orbitals. So when we look at this, I'm going to arbitrarily say that the sigma bond is in the center here. This is the sp orbital of this molecule atom overlapping and sharing with this sp orbital. The top and bottom bonds are represented as the pi bonds. So sigma in the center, pi on the top, pi on the bottom. Again, for the purposes of this class, you do not need to specifically designate however you want to do it. If there's a triple bond, two of those have to be pi bonds, one of them has to be a sigma bond. That's all I care about. So the triple bond, right, consists of a sigma and two pi. The lone pairs occupy the sp orbitals on each of the nitrogens. So we know that each nitrogen has two sp orbitals. Sp, 1, 2. So this nitrogen has 1, 2. This nitrogen has 1, 2. One of the sp orbitals from each nitrogen, they overlap, forming the sigma bond. The other sp orbitals on each nitrogen are where the lone pairs live. But now we need to still make our triple bond. Right now we only have a single bond. Here's our sigma bond. Now we have two unhybridized p orbitals. Now this happens on both nitrogens. So one set of the unhybridized p orbitals on each nitrogen will overlap with another, and giving us a pi bond this way and a pi bond this way. Now, we can go higher than that, right? We know that we can have more than 4 bonds around something. So now we're just going to start adding in the d orbitals. So if we were to have 5 bonds around something, we had a shape that was trigonal bipyramidal. We would call that d-sp3. Now, if you Google hard enough, sometimes you will see it as sp3d. It means the same thing. But basically what we're doing is we're still counting it out. If there are 5 bonds around, or 5 electronic groups around that central atom, we have to have 5 hybridized orbitals to do that. 1 from the s, 2, 3, 4 from the p, and the 5th one would come from the d. And give us a structure like this, just like we would see with our trigonal bipyramidal structure. So this is what we would see in something like phosphorus pentachloride, where we have a central phosphorus with 5 chlorines around it. Each chlorine has a set of the sp3 hybridized orbitals, because the chlorine, if we're looking at the chlorine right now, has 1, 2, 3, 4 different electronic groups around it. So each of these chlorines, right, each of these chlorines is sp3 hybridized. The phosphorus, which has 1, 2, 3, 4, 5 electronic groups around it, is dsp3 hybridized. So again, let's try this. I would like you to pause the video here and actually go ahead and draw your Lewis structure of triiodide, the anion. So I3-. Go ahead and do that, and then we're going to start looking at the bonding of it. So I3- should look something like this. Our central iodine versus our terminal iodines. Our terminal iodines are identical to each other. Our central iodine has 1, 2, 3, 4, 5 groups around it, electronic groups. So the central one will be the dsp3. The terminal iodides have 1, 2, 3, 4 groups around them. So each of those would be sp3 hybridized. That central iodide, when we look at it, has a sigma bond in each direction, but there are no pi bonds here. There's no overlap. The central iodide is just having those lone pairs living in the 3 other hybridized orbitals. As you can imagine, we know that we can have 6 things around a central atom. This would give an octahedral arrangement. So hopefully you've picked up on the pattern, but now this would be D2sp3. Let's count it out. 1, 2 from the D, 3 from 1s, and 1, 2, 3 for a total of 6 when we add in the p's. It's literally that simple. Again, each of these fluorines has 1, 2, 3, 4 groups around it, so the fluorines would be sp3, and the sulfur has 1, 2, 3, 4, 5, 6 groups around it, so it would be D2sp3 hybridized. Now, like I said, if you Google hard enough, you will also see this as sp3d2. Our textbook uses the D's in front. I would encourage you to stick with that nomenclature. And so it would look something like this. So I'd like you to take a minute again. I know this is a lot of Lewis structure practice, but it is good for you. Pause and draw yourself the xenon tetrafluoride ion or molecule. And then we'll go through and determine the hybridization on the xenon and the fluorines. So the xenon, right, it has 6 pairs of electrons around the xenon, 6 electronic groups, which means the xenon will be octahedral, which means the hybridization around the xenon would be the D2sp3. The fluorines are going to be sp3 hybridized because we have 1 electronic group here in the bond and then 3 lone pairs around it for a total of 4 electronic groups. Sorry, it's easier to see here. 1, 2, 3, 4. So each fluorine is sp3, and the xenon is going to be our octahedral, or the D2sp3. So again, when we're going through this, the best strategy to have is to draw your Lewis structure, and then once you have a good Lewis structure is to go through and determine the electronic geometry. How many electronic groups does it have? Remember, lone pairs count as 1 electronic group. A double or a triple bond, even though there's multiple bonds there, that only counts as 1 group. So here's a little bit of a relationship to kind of help us as we're going through this. If we have 2 electronic groups, that would be linear, which would give us sp hybridization. 1, 2, s1, p2. If we have 3 groups, we're sp2. 1 from the s, 1, 2 from the p for a total of 3. 4 electronic groups is sp3. 1 from the s, 1, 2, 3 for a total of 4 from the p. Trigonal bipyramidal, dsp3. 5 groups, 1 from the D, 1 from the S, that's 2, plus 3 more, 1, 2, 3 from the P. Octahedral is 6 groups, 2 from the D, 1, 2, 1 from the P, that makes 3, and then we have 3 more, 1, 2, 3 from the P. Sorry, it was 2 from the D, 1 from the S, 3 from the P, total of 6. So let's start looking at this with a little more detail. I'm going to go through these a little quicker now that we've kind of talked about them. If you need to at any point want to pause the video, draw them out, I really encourage you to do that. So we're going to go through and look at predicting the hybridization of each atom in the following molecular structures. So we have CO. We know CO is going to be linear. And in this case, the C and the O are both linear because we have a lone pair in the carbon. So lone pair for the carbon, lone pair, 1 group here, 1 group here, oxygen, 1 group here, lone pair here. So in this case, we have both of these as sp hybridized orbitals or atoms. So that this carbon will be sp hybridized and the oxygen will be sp hybridized. I'm going to tell you, and I'm picking that the central bond here is our sigma bond, and that the top and bottom bonds represent the pi bonds, or those unhybridized p orbitals overlapping. It would look something like this. Bf4 minus, we have to go through and draw our Lewis structure properly. Please don't forget your rules with your Lewis structures. These will be really important in making sure you draw the right structures. we end up with a structure like this. And we know that we have 4 groups around our central boron, which means our boron would be sp3 hybridized. We look to our fluorines and we count 1, 2, 3, 4 groups around those as well, so those would also be sp3 hybridized. It would look something like this. And then lastly, for the xenon difluoride, we have something like this for our Lewis structure. There are 1, 2, 3, 4, 5 electronic groups around the xenon, which means we're going to have 5 molecular groups. So this would be our dsp3 hybridized xenon, and we have 1, 2, 3, 4 groups around each fluorine, so an sp3 hybridization around each fluorine. It looks something like this. I'm going to just kind of go through each of these. Obviously, I put answers down for each of these questions. I would really strongly encourage you to actually read them, go through them, pause the video, answer them as you go on. So I'll pause, then I'll go to the answer one, pause, and go to the answer one, so on and so forth. All right, so this is the end of our Chapter 9, Section 1 hybridization lecture slides. I would really encourage you to actually go through this video a few times. Try these problems on your own. This is not something where you can just absorb it like a sponge. You do have to do it on your own as well. The homework will be really helpful for this, and I've also posted in our Unit 3 resources extra help section. There are a ton of really great videos that kind of animate what the hybridized orbitals look like, which make them a lot prettier than what I can draw. So I would really encourage you to check those out, and then as always, if you have questions, email me. Set up time for office hours. Let's get you guys set up for success.